In part one, we laid the groundwork for this method called partial fraction integration, sometimes called partial fraction decomposition. Now we're going to go through a bunch of examples of how to use this technique when you have a rational expression that you're trying to integrate. Now, it's worth kind of taking a step back here and just sort of seeing the big picture of the techniques that we've learned so far. The first integration technique that we looked at was for dealing with integrals when you have, let's say, something like this. The integral of e to just plain x is, of course, a nice integral, and it's very easy to evaluate. As soon as you get something other than just an x sitting up here, that's the time when you need to consider doing u-substitution, where you let this be e to the u, and you go through the process of writing a simpler integral. The second thing we looked at was how to deal with situations like this, where you've got an integral and it's made up of a product of two functions. When you have that sort of setup going on, that's when we switch and we do the integration by parts, where we're choosing a u and a dv. So this next technique, this partial fractions, is specifically to undo the quotient rule for derivatives. So what you're going to see in a problem that is going to lend itself to partial fractions is you're going to see a quotient, except most often you see it expressed as a fraction. So that's kind of how I look at this problem and know that partial fractions is a good candidate for evaluating this integral. The first thing you're going to do when you approach any of these rational functions is go back to kind of our guideline table here and check if it's proper or improper. So for this particular rational function, this is a proper rational function because the degree of the numerator is 1, the degree of the denominator is 2, so the numerator degree, which we sometimes write this way, the degree of the numerator is less than the degree of the denominator. So this is a proper fraction. Therefore, I don't need to worry about this first step of performing long division. I'm going to jump right into this table. The next step is to look at your denominator and see what type of denominator you have. I have a quadratic. I have an x squared. So in terms of my table, I'm looking at these situations here. But notice it says the quadratic is irreducible, meaning it can't be factored. So what I need to check is, can mine be factored? Okay, so back we go. I think about how to factor x squared minus 2x minus 3. I need a pair of numbers that multiply to give me negative 3. Same two numbers have to add up to negative 2. Is that possible? Yes. So I'm leaving my numerator the same, and it's possible to factor my denominator into x minus 3 times x plus 1. And you should be able to check that just, using FOIL, multiplying it out. X times x is x squared. You're going to get a plus 1x and then a minus 3x, which is minus 2x, and a minus 3. So these two are equivalent. And my quadratic, therefore, is not irreducible. It's reducible. I was able to make it simpler and write it as a product of linear factors. So I'm going back to my table now, and instead of worrying about cases 3 and 4, which no longer apply, I have linear factors. Now, I don't have repeated linear factors. Repeated linear factors would mean you have several of the exact same linear factor, like x plus 2 and another x plus 2. I have the first situation where I have two different linear factors. So the partial fraction form for this rational function is going to be this. So what I'm going to do is I'm going to leave my integral and I'm going to work on just writing the partial fraction form. So again, this is going to be entirely algebra. This has nothing to do with actually integrating. So I'm going to take and say the fraction I started with is this 5x minus 3 over x minus 3 times x plus 1. And the proper partial fraction form is I can split up the linear factors into two separate fractions. This formula says is my numerators in both cases will turn out to be constants that I don't yet know the value of. So I'm going to put A here and B here. You'll always use capital letters to represent these unknown constants. Now, I don't have to sit here and guess what to choose for A and what to choose for B, so that when I combine these, I get 5x minus 3. There's an algebraic process I can follow here. What I'm going to do is I'm going to work on the right-hand side the same way that you saw us do in the last video when we were trying to verify relationships. We looked at the right-hand side and we said, okay, if my common denominator is this, x minus 3 times x plus 1, this first fraction has the x minus 3, I need to multiply it by x minus 1 to achieve that common denominator. What I do to the bottom, I will need to do to the numerator. And my apologies, that's supposed to be a plus 1, not a minus 1. Now I have the x plus 1 denominator in the second fraction. It's missing the x minus 3 factor, so I'm going to put that next to the denominator, but I must also do that to the numerator. So I'm trying to add these two fractions together. My first numerator, I have x plus 1 times a. I'm going to put the constant in front because multiplication is commutative, plus, and then I have b times x minus 3. And now, since I have a common denominator, I can make this all into one fraction where I have x minus 3 times x plus 1 as that common denominator. I'm going to go ahead and use distributive property in the numerator. Now here's where you want to reintroduce the left-hand side. So what you're now going to do is compare the numerators, because your denominators are identical, so you can essentially disregard them at this moment in time. And I know that I have to end up with a 5x as a result of adding my like terms on the right. I have an ax and a bx. So I'm going to group those like terms, factoring out the x from them. So I'm going to have a plus b times x. This is equivalent to ax plus bx if we distribute the x back in. Then I have a constant term in the numerator, this minus 3, which has to be the result of adding these two constants together. There's no x's in these terms. These are just numbers. So again, I'm going to kind of group them together. A minus 3b is going to have to turn out to equal this negative 3. So the only thing I've accomplished in this step is going to the last step and kind of grouping my like terms together. And what I now know is that whatever numbers a and b are, when I add them, it has to turn out to equal 5. And when I do a minus 3 times b, I have to get negative 3. So I now have a system of equations. I'm going to take the 5, just the coefficient, and say that has to equal a plus b. I don't need the x's in there. They're already there, they're equivalent. I need to focus on the coefficients. So 5 has to be the result of adding a and b. And then my other equation is that the constant a minus 3b has to equal the constant on the left, which is -3. This is a system of two equations with two unknowns. So that is a solvable system. Now again, it may have been a while since you solved a system of equations. So here's one technique for doing that. We'll take a look at a couple. But when I have two different variables, very often I'll focus on the easier looking equation. This one seems friendlier than this one. And I'll get a variable by itself. So I can get a alone relatively simply by subtracting b on both sides. This gives me the statement that 5 take away b is the same as a. I can now substitute this value of a into the second equation. I'll have 5 minus b, replacing a, bring down the minus 3b, equals -3. Combine like terms, so we have 5 minus 1b minus 3b is going to be minus 4b, equals -3. And then finish solving for b now that you have a single variable in the equation. I've determined that b is going to have a value of 2. Once I know what b is, I can go back. Again, I usually prefer the simpler equation. I can substitute my b value of 2, and I'm going to be able to solve for a. So I've just solved a system of equations. If you have two variables, you need to have two equations. If you have three variables, you need to have three equations. So I now know what my a and my b value are, going all the way back up, so that I can split up this single fraction into two individual fractions. So in other words, my integral now, in place of the original, I'm going to have two integrals. One is the integral of a over x minus 3 dx, plus the other fraction is going to be capital B over x plus 1 dx. And by solving the system of equations, I got my a and my b values. So this process of taking this first rational function and splitting it up into simpler rational functions is what we call partial fraction decomposition. It begins by figuring out the general form for the particular kind of fractional expression you have, and then creating a system of equations to solve for your unknown constants. Now, once you've done that, this is all algebra over on the right. Now back on the left, I'm ready to do integration. And usually at this point, you're looking at doing a u-substitution. So for the first integral, I would let u be my denominator. I take the du of that, and I get dx. And again, I'm going to switch to the letter v here, but don't be confused. I'm not doing integration by parts. I'm just using another variable. In fact, let's just call it w. What the heck? So let's let w be the denominator of my second fraction. So dw is going to be dx. I can now write these using u-substitution. So I'm going to, at the same time, pull my constant in front. So I have the integral of 1 over u du plus, pull my constant out in front, 2 times the integral 1 over w dw. Those are both nice simple integrals to evaluate. So we have 3 natural log of u plus 2 natural log of w. I can throw on my constant. And the very last step in this process is now to replace the u with the x version. Replace your w, and you will have your final answer, which I'm going to make room to write. 3 natural log of the absolute value of x minus 3 plus 2 natural log absolute value of x plus 1 plus c. All right, so again, step back and look at the big picture. We took a rational function, a proper rational function. We found a way to split it into two simpler rational functions. We were then able to use u-substitution to evaluate each of those individual integrals, and that landed us here at the finish line. As a second example, we have this rational function. Now, the first thing we need to do is again determine if this is a proper or improper fraction. So I need to look at my degree of my numerator and my degree of my denominator. Your denominator is bundled up. You've got x plus 2 squared. So you do need to understand what that would look like as just a regular polynomial. In other words, if we multiply it out. So x plus 2 squared, do not just square the x and square the 2. Please remember, squaring anything means multiplying it times itself, and that's going to require us to actually FOIL that out. When I finish, I can see my degree of my numerator is smaller than the degree of my denominator, so this is in fact a proper fraction. Again, that's good news. That means I don't have a long division step on top of all the other algebra in this. So next, I need to go to the chart and figure out the general form for the partial fraction decomposition for this integral. So I'm going to go back up. And we need to look at our denominator. Do we have linear factors, repeated linear factors? Is it quadratic irreducible? I have written my denominator two different ways. I have it here as x plus 2 squared, and I have it here as a quadratic. This quadratic, though, is reducible because it originally started out as x plus 2 times x plus 2. So what I actually have in my denominator are linear factors, and they are repeated linear factors because x plus 2 squared means I have x plus 2 times x plus 2. So when I go back to my table, I'm looking at the situation now where I have repeated linear factors. My partial fraction form then is going to be made up of individual fractions, where first you write just the plain linear factor, then you write it to the second power, then to the third power, fourth power, up until whatever exponent you have. So what I mean by that is, when you have repeated linear factors, you're going to make a fraction where you just use the basic factor, x plus 2, that's technically to the first power. And then you're going to create additional fractions where you increase the exponent up to the exponent that appears in your original. So I'm now going to make the next fraction have a denominator of x plus 2 squared. Since I'm at my exponent, I stop there. But if I had a cube down here, I would put on another fraction. Fourth power, put on another fraction. And the table says anytime you've got linear factors in the bottom of these fractions, your numerators are going to be just constants, a and b. I'm going to work on the right-hand side and try and combine these two fractions into one by getting a common denominator. When I look at fraction a, it has a denominator of x plus 2. My common denominator is x plus 2 squared. I need another x plus 2 here. The second fraction already has the proper common denominator, so I'm not required to multiply this one by anything. It's ready to combine with the first fraction. So in my numerator, I have my constant a times x plus 2. I can now add just plus b all over my common denominator, x plus 2 squared. Carry down the left-hand side. Now I'm going to distribute. So on the left-hand side, we have 6 x's. There's only one term with an x on the right. So immediately, just by comparing coefficients, I know that a has to equal 6. Now I look at the constant term on the left, which is a plus 7, and I look at what I have as the constant term on the right, which is the 2a and the plus b. I know that those two have to be equal. I can substitute what I know a is equal to, and then I have an equation that has only one variable, which is easy enough to solve. So I have solved my system of equations to identify my unknown coefficients for my partial fraction form. That means I'm now ready to go back to performing integration. So first I've written out the separate integrals with the unknown constants. I do know their values now, so that will be the next step, is to put those in. And by doing the techniques in the last video, you would be able to confirm that when you combine these two individual fractions, you would in fact get the fraction on the left. Before I proceed with my integration, I'm going to take my constant in front, so I have 6 times the integral of 1 over x plus 2 dx. I'm going to take minus 5 out in front, leaving 1 over x plus 2 squared dx. So I'm going to perform a u-substitution, letting u be x plus 2 and du be dx. I'll do the same on the other side. Again, I'm just going to choose a different variable. I now write the simpler integral. And be careful, it is a w squared because w was x plus 2 and there's a squared on it. When I perform my integration, 1 over u du is the natural log of u minus, now this integral here, this fraction 1 over w squared, that does not become the natural log. 1 over w squared is the same as w to the negative 2 power. So what I want to do is actually use power rule on this integral. So I keep the minus 5. Power rule says take your exponent, which is negative 2, add 1 to it, so it becomes negative 1, and divide by that new exponent. So I'm using a different rule on this one because I don't just have 1 over w, but I have 1 over a power of w. And of course, we would put on our plus c. And then all that's left is to clean up a bit. I have negative 5 divided by a negative 1, so that's going to be a positive 5. W was x plus 2 to the negative 1 power. And this would be an acceptable answer, but honestly, if you were going to look this up in the back of the book, they will take this negative exponent and most often write it as its fractional equivalent, meaning your final answer would probably look like 5 over x plus 2 plus c.